So my name's Roger. I'll be leading the discussion today. And I see we have 34 folks signed up so far. Welcome to everybody. I made the mistake of, I don't know, a few days ago saying welcome gentlemen to a group, and boy, I got in trouble on that. So ladies and gentlemen, nice to see all of you here. Brian, I notice you're here 3 times, but I guess maybe you'll get 3 times as much out of it that way. Whatever. Okay, we are here today to talk about the essentials of photovoltaic system design, the 2021 version, which is still pretty much the same as the 2023 version. I can affirm that because I've reviewed 5 sets of plans today so far, and they look a lot like the ones we're going to be talking about today for the next 2 hours. I'm curious, though, before we get started too far, and if you would, I'm going to take a look at my participant box, and I think you have the ability to raise a hand. And I'm curious how many of you are already involved in the design of photovoltaic systems. It's important for me to take note of that because the level of the presentation can shift one way or another to make sure that everybody's getting what they need at the level they're looking for. So I say Ava and Jerry are, and Nancy. Oh, here we've got a lot of people. Kanar, Matthew, oops, Brian. We have 6 people, just out of curiosity, or 5. If you would, let's start with Jerry. Jerry, tell us what's your involvement in photovoltaic system design? Now we're down to 4. Can you unmute and do that, Jerry? And the other thing that I'd like to ask is that we reserve the chat box for communication with the host, just in case there's any technical issues involved this afternoon. And let's carry on our conversations under Q&A, questions and answers. That way, when I see something flash up on questions and answers, I can go to it. And if something shows up on chat, then I'll know that somebody is working something out with the host. So I'm assuming everybody can hear me. I was going to say, if you can't hear me, raise your hand, but that maybe wouldn't make much sense. So Jerry, would you tell us what you're doing in the photovoltaic business? What is your specific job function? That's Jerry Borbach. What's happening with microphones here? Maybe everybody is muted because there's so many. Let's use the chat box or the Q&A. If you're involved in photovoltaic design, if you just type in under Q&A what you're doing. You do design work, plan review, inspections, whatever it might be. Just type it in so I'll have an idea, okay? And meanwhile, we'll, okay, there we go now. Okay, John's curious. Brian does power system design with solar PV by others. Okay, others do that. Okay, good. Oh, okay, and plan review for your own home. Okay, design foundations so that, foundations and trackers. Boy, we could not get along without you guys, that's for sure. Racking analysis, structure. Okay, Nancy, that's terrific. Yeah, we get some interesting. I'm down in Florida. We got 175-mile-an-hour winds in Miami with exposure D in some cases. That's a real fun analysis. I'm sure you'd love it. And then you work in building design, conduct plan review. Okay, all right. That's great to have that. I'm going to click some things here, just so I don't confuse myself with future discussions. I have to type that I answered live, and then I have to type done, or click the done signs. That's a lot of responses here. I forgot about that part. Okay, that gets through the questions, and we can start getting on with hopefully some of the answers. So what about why is photovoltaic systems, why are they even of interest? I mean, aren't they just way too expensive? That's the question that a lot of people are asking, or at least have asked in a long time. So let's take a little look at what's going on as far as the cost here. Since 1976, cost has come down by a factor of 300 for photovoltaic modules. So maybe that has something to do with the fact that people have an interest now. 1975, more than $100 a watt for a PV module. You would not put 10,000 watts on your roof at that time, probably. 2020, though, we're at about 40 cents. 2022, kind of leveling off here. As far as I can tell, there's different, depends how many you buy. If you buy lots of them, you get a pretty good price. And it also depends a little bit on what you buy, because some of them have stronger frames. I think down in my neighborhood, the cost is a little bit higher because if you want to withstand a, well, we'll be talking about pressures and wind loads. So we'll take a look at some typical numbers as we move through. So this factor of 300 doesn't even account for inflation. So if we talk about $20, it would be down by even more than that. So there's a way that people use in the energy business and a lot of other business, but energy in particular, for comparing apples and apples. I do see a question there. We'll come to that in just a minute. It's called the levelized cost of energy approach. And what that basically is a life cycle cost analysis, but it's how much do you have to charge for your electricity in order to pay for your investment of fuel and original infrastructure and final decommissioning over the life of the system, and maintenance, of course. And so natural gas now has an LCOE. This is, by the way, you look at the United States Energy Information Administration, comes up with these numbers. So it should be a pretty reliable source. So natural gas, we're down to about 4.4 cents a kilowatt hour. But if you're going to build an advanced nuclear plant, it's probably going to cost you 12.9 cents a kilowatt hour, amortized over the life of the plant. Onshore wind is down around 2.6 cents. Large scale photovoltaics, about 3.1. We're talking utility scale there, but if you get down to residential, that's a bit more expensive. And again, it depends on where, what exactly, but these are rough numbers, but relatively in terms of other energy sources, gives you an idea of why people are putting solar on their roof. And that applies to residential, commercial, and especially the utilities. About 80% of the new photovoltaics being built worldwide is utility, and particularly in the United States. So just an idea of how people might make these judgments as to whether they want to get into the photovoltaics. Let's look at a couple of questions up here. Cost with or without government subsidy. This is without the subsidy, and it gets better with the subsidy, as you know. And okay, Nick, I didn't. You need the CEUs, and I guess a lot of us needed them. Well, some of us had to be done before the end of February, or we were out of business for the next 2 years. But in any case, so, and by the way, these numbers, you'll look them in different places, and you'll get different answers. And the reason is there's a magic number in here, the utilization factor. For example, if you built a plant, but you only use it for peaking energy 5% of the time, then you got to make all your money on just having it run 5% of the time. If you have large scale PV that runs whenever the sun is up and you capture all that sun and use it and sell it, then that's different from if you just use that PV energy between the hours of 9 and 3 or something like that. So I don't know exactly what the assumptions are here. The best I can do is assume that they're trying to do some averaging on natural gas plants. Natural gas now is a very, very dominating force in terms of energy production. Utilities are switching over rather rapidly from coal to natural gas, so it's going up fast. Okay, there's another interesting thing that's in my mind is really important, and that is the PV energy return on investment. That is, if you invest a kilowatt hour in producing photovoltaics, how many kilowatt hours will you get back as a result of that investment over the lifetime of the cell? Okay, and in 2017, depending on the particular technology, this number was somewhere between 10 and 30. And it also depends on the location, because if you're out in the desert somewhere, or either a northern desert for that matter, where you get more sun and it's cooler and this the performance is a little higher, you may do better than if you're in a hot and rainy climate where it's pretty cloudy or something like that. So depending on the number of kilowatt hours per kilowatt per year you can make with your source, that will affect the amount of kilowatt hours you get back over the life of the cell. But then again, there's some interesting question here, because what is a cell lifetime? And most people put it down as 25 years, but an automobile might have a so-called lifetime as long as you keep it 10 years, but it's going to last a lot longer than that. So these numbers might be lower than they really are, depending on the assumptions, but or even higher than they are, depending on the assumptions. But 10 to 30, anything better than 1 is a good number, but better than 10 is an even better number. So that's another, because this energy return on investment is increasing, that's another reason why prices are coming down. And of course, then again, shipping is costing a little more, but then again, we're making more cells in the United States now. And, you know, the whole supply chain thing affects what's going on here, as everybody on this particular call happens to know. But cells and modules, the production is more efficient. Big breakthrough in the manufacture of the silicon around 2009, 2010. A whole lot less energy intensive process after that point, brought the cost of the modules way down. We'll finish this slide and then we'll take a look at the question. And the cells themselves, they're becoming more efficient. The first systems I was designing back in the somewhere 2000 to 2005 time frame were roughly 13% efficient. So now when they're 20% efficient, that's not 7% more efficient than the previous one. That's 50% more efficient, because in the same space, you can now deploy 50% or harvest 50% more energy. Just because the cells are 50% more efficient than they were 15, 20 years ago. So a lot of exciting stuff going on out there, that's for sure. Let's see the question. Yeah, okay, your systems have a lifetime of 35 to 40 years. So there's the answer. Multiply. Of course, then you can argue that the cells do degrade somewhat over time, although it's pretty hard to measure it. So people just, in fact, the warranties on cells have been raising the bar on what they're going to be doing 25 years from now. They used to promise 80%. Now they're promising more like 90%. So yeah, figure at 40 years, if they're still 80%, then 10 and 30, let's make that 20 and 60. So thanks for the comment. And I always like comments that substantiate my claims. I guess we probably all do. Okay, so not only are the cells becoming more efficient, but the inverters and the balance of the system energy costs are decreasing. The electronic part, the cost of copper is not going down by any means. So the wiring itself, that's getting a bit more expensive. And maybe the labor is going up. It'd be nice if it did help pay for increased cost of food or whatever. So let's look at and see what kind of PV systems are there. There's standalone systems, and you've all seen them, highway signs and stuff, highway warning things, you're going too fast, whatever. Oftentimes they're run on PV if it's hard to connect to the grid. And there's grid connected. This is an old grid connected system up in, maybe if anybody up is from the, up in the Adirondacks area, this is in Tupper Lake at a nature center. And it was there about, I forget when I was there, 12, 13 years ago, this system was up, and it's pretty impressive. And this other one on to the left, that's pretty clearly standalone. And you can get a pretty good guess where that is by the tilt of the modules. They're almost vertical. And where in the world does the sun shine almost horizontally? And of course, that's Alaska. And I can't, this is either the entrance or the exit to the exit glacier down on the Kenai Peninsula. So it's not necessarily a requirement that PV installed in beautiful territory like this, but there's quite a bit of it out there in nice places. A few other examples. Here's a system in Nevada. I have good reason to, but this is probably a standalone system. It's at the Great Basin entrance to the Great Basin National Park, Utah. There's some weather stations run on PV. You see these all over the place. And these are tilted a lot higher than they most need to be for Utah. But you see similar ones in Iceland and all over the place. Wyoming has their own sign PV systems, and just got to watch out for this big game out there in Wyoming. And thank goodness we have PV powered signs to warn us of that. And they probably a whole lot more deer make it through the winter without getting hit by whatever. Anyway, not that Massachusetts doesn't have their PV, and not that Yellowknife Northwest Territories in Canada doesn't have their PV. And then there's commercial rooftop, and there is utility scale stuff out there. And so, you know, it's out there, and I'm sure you've all seen it, but it's always fun to look at a few pictures before we get really serious. And so now you better roll up your sleeves a little bit, because we're going to get ever so slightly more serious and talk about the sun. The peak sun intensity is about 1,000 watts per square meter. Now, probably most people don't think about the peak sun intensity in terms of watts per square meter. Maybe it's in terms of foot candles or something like that. You know, a camera bug wants to know what's the light intensity. But if you're going to make electricity with it, you might as well recognize it in terms of the amount of power that's available. And so we're looking at every square meter of sunlight where the sun is shining directly down on it at sea level. If you go up 18,000 feet, you get a little bit more. And there are other ways of focusing with clouds and so forth, but the accepted value for peak sun intensity is 1,000 watts per square meter. Not 1,001 or 998. It's amazing that 1,000 seems to be the number that folks have zeroed in on. Depending on technology, you can convert about 20% of this to electricity. Most of the technology out there right now is silicon. There are some other multi-layer technologies where you capture different wavelengths and different layers. And then by doing that, you can increase your efficiency to the high 40% ranges, but it's pretty expensive and it's very spectrum dependent. So if you have a cloud go across the sun that absorbs certain parts of the spectrum, in any case, it's great in outer space. but you don't see much of it because it's pretty expensive down on the earth. And the annual conversion range, and we don't talk about in terms of the number of watts. What we're really interested in is how many kilowatt hours per year do you get for every kilowatt of photovoltaics that you've deployed. So if you're in Florida facing north at say 25 degrees slope, you might convert about 1,000 kilowatt hours a year for each kilowatt facing north. And I say north because it's incredibly different from anybody who's been around for 20 years, even imagining north-facing solar being cost-effective, when in fact, you can now make electricity in Florida with a north-facing array with a LCOE of about 7 to 8 cents a kilowatt hour. So people are installing on north-facing roofs, and the simulations look good, and the actual performance matches the simulation. So that's very interesting stuff. If you go out in desert, get out certain areas where you get some really good sunlight, or for the person who in the group who designs tracking arrays, if you've got a good tracker, you might very well come up with 2,000 kilowatt hours per kilowatt per year. Of course, then you need to watch out for shading, and then you start talking about, well, how about kilowatt hours per kilowatt per acre per year? And assuming land costs, those things can get interesting when you do the math on these systems, but we're not here to talk about doing that math. We're here to talk about designing the systems themselves. I see we now have 43 participants. So once again, for anyone who came in a little bit late, we're conversing by way of the Q&A. So if you have comments or questions, type them into the Q&A, and we'll see them there, and I will respond as I might say we're going to talk about that later. I might say I have no idea. What do you think? But you'll get some kind of an answer. That's true. There are some very sophisticated performance models out there, and almost everybody uses them now, compared to long ago when we simply guessed at how many peak sun hours there were in a day, and we just don't do that anymore. So let's talk a little bit about solar photovoltaic module electrical properties, because the design itself is important. And what I'm trying to do here today is get everybody to understand how this stuff works, because the world is changing very rapidly in the photovoltaic area. Enphase comes out with a new microinverter almost, who knows, every 2 weeks, maybe not that fast, but it seems like it. and other people come out with other things, and so it's quite a challenge to keep up with the market these days as to exactly what's out there. But if at least you can understand how it works, why it works, and whether it's useful to use based on some basic knowledge of the fundamentals, that's what we're going to shoot for today. But we're going to talk fundamentals using modern systems. All right, so notice first, one thing you might notice is that if we look at the current versus voltage curve for different sunlight intensities, you notice that it's almost linear, isn't it? For 200 watts per square meter, you get about 20% of what you get for 1,000 watts per square meter. Okay, and this is a module. Let's go down to 0 voltage, for example. You probably note that at 0 voltage, power is voltage times current. So even though that voltage is up there, if no current is flowing, they're not making any energy or electricity, any power. Okay, but as you move up the voltage scale to 20, 25, 30, the current stays pretty constant. It's just like a constant current source, up until you get here in this particular case up around 40 volts, when all of a sudden the current starts dropping off. And for anybody who has an electrical engineering degree, this just happens to be in the third quadrant of the diode voltage current characteristic. And if that means nothing to you, just pretend I never said it. All right, but you can't teach electrical engineering for 35 years without remembering at least something. So the key here is that current is pretty much linearly dependent on the sunlight intensity, but the open circuit voltage, that does not look at all like a linear dependence, does it? And the fact of the matter is, it's pretty much a logarithmic dependence. And I know that if I had asked that question, probably more than half of you would have said, oh, that's obviously logarithmic dependence, Roger. So this is what the idea then is, if there's zero power for short-circuited module, another reassuring thing is if you short circuit this module in full sunlight, only 12 amps will flow, and hopefully you're not going to burn too much up, including the module itself. Or if you open circuit it, well, you touch your fingers across there, and given that a few milliamps can give you, well, let's say 100 milliamps can be a terminating experience. So you can see that you got to be careful with these things if the leads are open circuited. Well, fortunately, the leads have special connectors where it's really difficult to get your finger inside the connector and touch where the metallic termination is. So that's not as much of a problem as it was 30 years ago when you had to put your own leads on these things. So anyway, this is the characteristic of the module. The whole idea is you want to operate it at its maximum power point, and there are special electronic circuits that assure that this happens, and we'll be designing circuits with them, and we're going to be talking about maximum power point trackers. And you can see on this IV characteristic of the module where that maximum power point is, and we'll have an even better picture. The next one is coming up, but there's 4 numbers that are really important: the short circuit current, the open circuit voltage. That is, if you short the 2 leads together, the current will flow. If you leave the leads open and measure with the voltmeter, you measure a voltage. And then the maximum power current and voltage, both there's 1 point on the graph that represents that current and voltage that gives maximum power for a given sunlight shining on the solar module. If you look at VM and IM here, this is under standard test conditions, 25 degrees centigrade, 1,000 watts per square meter. You notice the VM times IM would give your maximum power. So let's look at that on the next one. If we simply plot power versus voltage, and all we did was multiply the current times the voltage in the previous slide for every point on the curves, and here's what you get. And you notice, interestingly enough, regardless of the sunlight intensity, the maximum power point happens at about the same voltage there, around 41 to 42 volts. Now, there's a kicker to this, though. This is provided that the module stays at the same temperature. But guess what? If you've got only 20% of that sunlight that shines on this module being converted to electricity, what do you suppose happens to the remaining 80%? Well, maybe 5% is reflected, but the other 75% is going to be converted to heat, which warms up the module. So as the module gets warmer, they just happen to have a negative temperature coefficient. And when that happens, we'll see in the next slide, but I want to point out also that maximum power point trackers are what these things, the first thing the module is normally connected to now is a maximum power point tracking circuit. And the amount of electronics there is relatively small because it can fit in a very small box. Okay, so let's look here. This is what happens with temperature. And this is why you kind of want to keep them cool. This is why when you paste a solar module directly to a roof, it tends to get a little warmer than if you keep it about 4 to 6 inches off the surface of the roof with a standoff mount. So notice here the maximum power point actually does drop in voltage, and so at really high voltage, or sorry, at higher temperature, 75 degrees C, you'll have a significant drop from the 25 degrees C, and also the maximum power at 25 C. You see, we've got about 440 watts. If you take 25 degrees off, cool it down a little bit, you're up closer to 500 watts, around 490. But if you raise it to 75 C, then you're only going to get about 360 or 370 watts out of it. So that's why the actual power coming out of a module is not nearly as important to the designer for anything other than verifying the performance of the module. But you almost never expect it to put out what it's rated to put out under standard test conditions, because Mother Nature doesn't offer those that often to the modules sitting on somebody's roof or in their backyard or in their field. Okay, so and what that means is you don't have to worry too much about blowing any circuit breakers or fuses, because if you size them according to the National Electrical Code, the modules are very much current limited, and you'd have to make the sun twice as bright or something. And that takes a pretty good magnifying glass. And if you want to make it twice as bright, you're going to have to focus 2 meters down into 1 meter. And that would take a pretty big magnifying glass pretty high above the module. Yeah, we've got those. They're called clouds. And sometimes that does kind of happen and give a 25% increase. But anyway, the negative temperature coefficient is roughly 0.36%, maybe it's 0.361226113% per degree C, but we just rounded off to 0.36. And so the bottom line here is this is the reason why it's a good idea to try to keep the array cool. And this is why an array that's standing up off the roof a little bit needs to be visually attractive. So we might have to train our eyes to appreciate that little spacing underneath the module, the idea that it's going to make your electric bill a little bit lower. What about orientation? Well, I'm guessing a few of you are up in Albany, because folks up in New England tend to have more requirements for live webinars. So let's look at Albany, and let's look at an array that is facing south with a tilt of 30 degrees, because that is the optimal tilt for Albany based on the simulations. And by the way, I'll give you the information on that at some point, but why not now? The National Renewable Energy Laboratories has a program called SAMS, System Advisory Model, and you can download it for free. It's paid for by taxpayer dollars. It's free download, so it's a great thing to do if you get bored with dinner time conversation. You download SAM, and then you can say, did you realize that in Albany, if you have your modules tilted at 30 degrees, you get the maximum performance of your system, unless you use a tracker. And that just livens everybody up at the dinner table when you come up with stuff like that. I mean, you guys are all engineers, you understand that. So in any case, or maybe some architects in the group, and architects, of course, think a lot like engineers. But what we're looking at here now is the numbers. If I'm that same array is facing south at 60 degrees instead of 30 degrees, you lose 7% on the year. If you have a 15-degree difference in tilt from 30 to 45, you lose 1%. You can lose that in the wiring. So the bottom line here is, because of all these numbers, the performance is fairly good, and that's why it's generally, from a wind loading perspective, from a aesthetic perspective, and almost every other perspective for rooftop arrays, generally they're simply put on with standoff mounts, as the example photos you saw. Except for the ones up in Yellen, I guess. But otherwise, most of the rooftop arrays are just standoff mounts about 4 inches up off or 5 inches off the top of the roof. And the reason is simply because you don't lose that much. And if you can put enough to power your entire house and have a little bit left over on your roof, generally most people are satisfied with that anyway. And that's for the most part what we're finding we're able to do here in Florida. And I'm sure that's possible in New York as well. We've done some simulations in other areas, and no reason why people in New York can't make 100% of electricity as well. Won't all be made at the time you need it, doesn't work real well at night, and so on. But overall, you can make as much as you use. You'll have excess in the day that you'll sell back, and you'll have to buy some at night. So anyway, it's just some numbers for you, and you can verify this if you download SAM. And the idea here is to just justify that it's okay if your array doesn't face exactly south at 30 degrees. You're still able to do fairly well. If you have your array a little bit off the optimal going south. All right, so let's look at grid connected systems. We are going to talk only about grid connected systems, and we're going to talk about grid connected systems without batteries. All right, there's a straight grid connect, and makes electricity when the sun shines and the grid is in operation. But if the grid goes down, the system has to disconnect, because after all, you don't want your electricity powering up those power lines. Well, some maintenance guy is up on up near the distribution line trying to repair it, and all of a sudden your PV system through the transformer, there's this at 12,000 volts that was not expected, and it's not very welcome to. So therefore, it has to disconnect from the grid if the grid goes down. But if the grid starts getting weak, that now is a provision that the utility can sign a special agreement with you that you will leave your system on if they're nearing their peak, and say their voltage or frequency is dropping near the limits where the PV is supposed to shut off. Well, if you have a 100 megawatt PV system and the grid starts getting challenged, and then you shut off that 100 megawatts, that's worse than leaving it on. So that's now covered in IEEE 1547-2000, where the utility can make those arrangements. And of course, the straight grid connect can sell back to the grid. But that's about it for the straight grid connect. The battery backup does all of what the straight grid connect does, but it also will disconnect from the grid and maintain a standalone and battery backup for the building if the building loses power from the utility, and that's historically. Now, the other part of the battery backup, again, since the year 2000, is that you can set up, if you have an appropriate agreement with the utility, you can set it up such that you can turn your batteries on during grid peaking time and sell some electricity back to the utility. It may never make it out to the utility. It might just power the loads at your own occupancy, but that's just as good. I mean, once those electrons are out there in the world, nobody knows where they came from or where they didn't come from. It's just a matter of having less current flow, and you can do that by turning your dryer off or turning off your water heater or your air conditioner, or you can dump some extra electricity out of your batteries from the backup in order to power up your water heater without having an effect on the grid. So there's some really interesting stuff coming up these days, and some of you may be aware, others may not be aware, but bottom line is stay tuned. There's some exciting stuff happening. So what about a properly designed and installed photovoltaic system? And am I talking too much? The 242. Wow, I might be. Let's get going here. let me just say that we'll have some stuff that has a lot of words on a page. And if that's the case, I'm going to go through that fairly quickly and get us to the pictures, because that's where you learn what's going on. Okay. So, and if this is something you want to pay more attention to, as you got from the chat box, all the instructions on how to download the slides, feel free to read these, use them any way you want. I'm the owner of the copyright, and what I'm interested in is education. That's my background, although I was electrical contractor and did a lot of photovoltaic system design. I'm still busy in that business. But my interest is learning and understanding. And if people use my material to teach somebody else, I feel I've done something useful. Even if you make some money on the deal, that's fine with me. So you need to meet electrical design performance. It shouldn't leak. It shouldn't blow away. It should look nice. It should last a long time, which means that if you have a warranty of 25 years on the modules, you better use stainless steel hardware and have a 25-year performance of everything else in the system as well. All right. And the other part is it should be at some point, depending on your relationship with the utility, we can help them out by providing them with some much needed electricity at times when they need it. So what are you going to need? PV modules. What a surprise. Some racking. Well, no surprise there either. And you got to do it right. Otherwise, you're going to have a leaky roof. We're talking about rooftop solar here. And so there's some reasons why people put in the backyard. They don't want to take a chance with their roof. But there are thousands and thousands of roof penetrations made every year, most of which, the high percentage, 99.99% of them don't leak. Unless the roof itself was in kind of bad shape to begin with. You need an inverter that's listed to UL 1741, because the modules make DC electricity and we need to turn it into AC, and it needs to be good AC that the grid will be happy with. You need code compliant disconnects, code compliant wiring, code compliant utility connection, or you need rapid shutdown provisions for emergencies. Code compliant, I don't know if I said anything, you need a permit for it. You can't forget about fire codes and other codes, building codes as well, wind loading codes. So this is the electrical part, but there's a whole lot of structural part that it has also needs to be code compliant. Need a permit, and you're going to have sign some agreement with utility that they will buy your electricity back from you. And there's some question now. The utilities are saying we're paying way too much for the electricity you're selling us. Although they seem okay to pay 30, 40 cents a kilowatt hour for peaking electricity when they have no other options. So there's a lot of discussion going along in those areas these days. And sooner or later, everybody's going to realize that we all need to be on the same page, and we'll come up with some agreements. Question here, let's see what we got. Our battery backup systems more common now. We have a system on our family farm, and battery systems were cost prohibitive 10 to 15 years ago. We're going to come to that. The answer is they are more common. I would say, let's just say a little personal experience here. Over the last 2 years, I've gone back to work for a former student. I have done plan review for about 4,300 sets of plans. And I would say about between 5 and 10% of those are battery backup systems. All right. And the fact of the matter is, if you have a straight grid connect, we will show you how to put in batteries and still say that straight grid connect. All right. Batteries still aren't cheap, but the batteries are fancy. They've got electronics in them. But a lot of people are buying them. They see them as a good investment. You can't really consider batteries for anything other as an insurance policy. If you got valuable things that you need to keep refrigerated, or if you have some kind of healthcare system you have to maintain. We still can't call these emergency systems. They're called backup systems. Emergency systems have to be fossil fuel, even though the PV systems, when the utility goes down, you have essentially a seamless, uninterruptible power supply with your battery backup system. We'll get there. So for now, I'm just going to say the answer to your question is yes. Actually, I guess I said more than that, didn't I? Thanks for asking that, Nick. So, looking at and we're not going to talk about battery backup systems, but your host does offer the battery backup follow-up to the Straight Grid Connect on occasion. So you may want to pick up on that and keep an eye out for when that might be offered, because I've just updated the battery backup version as well. So in any case, this is the string-fed inverter system. Notice that all of the modules are just connected in series, but I have two series strings, and those two series strings are connected in parallel. Why is that? Well, series, that means they all have the same current, and in parallel, they have the same voltage. So you have to have the same number of modules and the same sunlight exposure in all of these strings. Otherwise, the one bad module, since it's in series, just like one bad battery in its flashlight with two batteries in it, if one of them goes bad, the flashlight goes out. So if one of these modules goes bad, it takes down the whole string. And if one string goes down, it can affect the voltage of the second string. So one bad module can mess up the whole array. But let's say everything's working fine the way it's supposed to. And we've got these modules here. They simply deliver DC down to the inverter, which is generally at ground level. And the inverter converts it to AC. There's generally a disconnect at the inverter output. There's also usually a disconnect built into the inverter for the input of the DC. And once the AC disconnect between the inverter and the distribution panel, with the PUC means point of utility connection. So this may be a backfed circuit breaker. We're going to look at a number of options for tying into the utility as well. So this is a string-fed inverter. There's certain the advantage is it's the least expensive because there's no fancy electronics up on the roof. It's all downstairs. But what you pay for that is if a cloud covers a couple modules, then you lose significantly more than just those two modules. So your overall annual performance is going to be affected with this system. So then along came the folks who invented microinverters. It started out, people said, well, let's just put the inverter in the module right underneath it. And they did that, and then they realized the inverters were less than 10 years, and the modules were less than 25 years. So these so-called AC modules kind of went into dormancy for a while. And then along came but the microinverter people persisted to the point where now you can buy microinverters with 25-year warranties, which makes some of the module manufacturers happy, and they incorporate the inverter, and you buy the inverter with the module. And that's called an AC module, because what you get out of it is AC. So in the microinverter system here, you can see the DC goes into the microinverter, and the microinverter connects to two wires, line 1 and line 2, and the output of that microinverter is 240 volts AC. Now that's residential. It could be 208 if you got a 120, 208 service, but typically the large majority of the systems are using 240 volts, and that's straight 240, not a split 120 240, but just 240 volts. But notice they're all connected to 240 volts. The output voltage of all of these inverters is essentially the same, except for a very small voltage drop in the wiring between them. So that means these microinverters are not voltage sources. The voltage that they work into is provided by the utility. So they're current sources, and you can do that electronically. But current sources are not something people are familiar. You plug something into your wall, that is a voltage source that you're plugging into. You put a battery into your car, that is a voltage source. Your batteries and your flashlight are voltage sources. You don't go to the hardware store and say, I want a 5-amp current source. They don't sell those things. But you can get that, you can do that electronically. And that's what the microinverters do. It's current. So let's say the first one is putting out 1 amp, and the next one's doing 1.1 amps, and the next one's doing 0.5 amps, meaning the first 3 modules have different exposures to sunlight. Nobody cares because each one does what it can, and the current that comes out of the microinverters just adds up, and you get everything you can possibly get given the exposure conditions, without any one module messing up the performance of another module. So that's a major advantage of this system. Okay, and there's another system similar that we're going to look at as well. So now we've got AC coming down from the roof. And that's interesting as well, because AC could conceivably come down as a piece of Romex, but most installers bring it down in PVC conduit. Well, if you go to the DC coming out of the junction box in the string fed inverter, that's got to come down from the roof in metallic conduit if it goes through the attic. And not just does it come in metallic conduit, but it has to have a label on it every 10 feet that's saying it's a DC power source. And you don't need to do that with an AC power source. So it's just another technical, that doesn't mean it makes more electricity. It's just a little bit easier for the install if you can run PVC rather than having to bend metallic conduit or use flexible metallic conduit. That's allowable. As long as it's metallic. The other system that's relatively popular these days uses this thing called optimizers, and these are like DC transformers. And almost everybody knows that you can't put DC into a regular transformer and get DC at a higher or lower voltage out of it. They only work with AC. But electronically, there are things called DC to DC converters, and you can put DC at one voltage and one current into it and get DC at a different voltage and a different current out of it, such that the input power, volts times amps, equals the output power, volts times amps. So notice the difference here. This is a series connection now on these optimizers, not a parallel connection like we had with the common voltage. For the microinverters. Here in the optimizers, we have a common current, but each of those modules, since each of those little yellow boxes contains its very own maximum power point tracking circuitry, there will be, if they have different exposures, they will all operate at different voltages, but they have to operate at the same current because they're in series. This is the output current. The input current can be less, but ultimately, so here's the interesting thing now. I mean, the whole thing is interesting. I can't say that one thing is more interesting than the other. That wouldn't be fair. But if we take a look now in that junction box, and as we go down to the inverter, these series strings are connected in parallel. So the voltage of each string is the same as the voltage of every other string. Okay, and that's controlled by the inverter. And the inverter does sort of an iterative process in order to optimize the production of the entire array. The typical operating DC voltage here is roughly 400 volts. Unless you're going into a commercial 1,000-volt system, then your operating voltage for the optimizers is going to be up around 850 volts. Okay, but residential optimizer systems, somewhere around 400 volts. Okay, so, and again, pretty much the same stuff down at ground level, except here's where your inverter is. The inverter is not on the roof under the module. It's now down below, and it has to be capable of handling the total power of the array. If it can't, well, you can always put more than one array up there, 2 of them, and use 2 inverters, or 3 or 4 or 5, and you combine the outputs of the inverters, run that into an AC disconnect. That feeds into the distribution panel. And sometimes that AC disconnect will simply be a backbred circuit breaker in the distribution panel. It depends on the size of the system and local ordinances and local rules and stuff like that, and utilities. Anything you don't use on site, you can sell back to the utility. So there's your optimizer system. Wait a minute, where'd I go? Oh, we're going to start the design now. My slide advance is a little touchy here. Usually the design starts with the module unless it starts with something else. That may sound crazy, but it is possible to do these things every other which way, and it's generally an iterative process before you end up with the final result anyway. So a lot of times the way you start is you simply figure out how many modules you want to put on your roof, or see if you can fill your roof with modules to the extent allowed, or maybe you have a favorite inverter that you want to use, or favorite microinverters, or maybe you just want to use one roof, or maybe you just want to supply whatever the reason might be. But if you have a module, then the folks who inspect these things are fussy, and they have to be listed to the Underwriters Laboratory 1703. Okay, and that's a fairly comprehensive listing in terms of structure and electrical performance and so forth. Well, you know about the electrical properties. We showed you a picture of that, but they also have thermal properties, and we showed you that, in fact, they do in the electrical picture. And also they are structural. Some are rated at maybe 50 pounds per square foot, and others have ratings up as high as 75, and some are even over 100 pounds per square foot. But you can pay a little bit more for those with the higher ratings because they obviously must have stronger frames. So let's pick one. Can't have any fun unless you choose something here. Here's a standard module, 65.9 inches long. Why that strange number? Well, that's just about 2 meters. 39.4 inches wide, that's about a meter. So 1 meter by 2 meters is pretty common, somewhere close to that. 1.34 inches thick, 18 square feet area. Most of the modern modules that are in the 350 to 460 watt range have areas somewhere, surface areas somewhere between the 18 and 22 square feet. The listing, 5,400 newtons per square meter, that's 113 pounds per square foot downward. Most of them have that, and it's because of the way the frames are designed. They are stronger if you push down than if you push up. And 75 PSF uplift. And the wind loading, it's the uplift that we get concerned about, because just like an airplane, it's not the wind underneath the wings that holds the airplane up. It's the suction above the wings that holds the airplane up. And it's the suction above these modules that tries to lift them up off the roof. And that's an interesting revelation in itself. And 75 pounds, that's pretty good. And it works for most of the systems that we design here in South Florida if we have 2 rails for mounting. So let's talk about roof zones. Some of you might be familiar, but zone 1 is the inside. That's where the least amount of wind is. Zone 2 is at the ends and the edges, and there's generally a little more there. And zone 2 is broken into zone 2 edge, or 2 eaves, 2 roof, 2. There's generally 3 different zone 2s depending on the roof configuration. But they're at the ends, and then there's the corners. And the locations and the definitions of these zones depend on this thing A, this quantity A. And you can read this definition 10 times and you still maybe walk away wondering exactly what it means. 10% at least, and I'm going to read it to you if you really want to know what it means. It's the dividing line between zones, and it's how you calculate it based on the geometry of the building. Okay, now ASCE 716 has added more roof zones than 1, 2, and 3. and it depends on the type of the roof and the slope of the roof. So a very handy reference to have at your side or on your computer in electronic form is ASCE 716, along with the National Electrical Code and maybe some fire codes and a few other state building codes can come in handy as well. Okay, so once you pick the module, then you want to see if it'll fit on the roof. Now, maybe you're going to draw your roof to scale first and add the roof zones, okay? And it might look something like this. And maybe you want to keep the wind resistance at a minimum in zone 1. It turns out you don't really have to do that usually, except in some very special cases. But if you can keep what you need and what you want in zone 1, then you don't have those extra pressures that are generally present in zone 2R and zone 2E in this particular hip roof configuration. Okay, so draw it to scale, and that in itself gets to be fun, but there's lots of tools for that, like drones, for example, that can take very nice pictures looking straight down at the roof. So you can get the exact correct dimensions. And so you add some modules. And maybe it'll look like this. And you see some of those modules are encroaching on other zones. Down at the bottom there, some of those are in zone 2E. And some of the others have little parts of them in zone 2R. And so what you do is you do an averaging of the forces on the modules, a weighted average of the forces on different zones to get your total force on the module. And then you have an idea what it's going to take to hold it down. Okay, so you add the modules, then you determine the wind load. And when you do the wind load, there's certain things you need to know. The mean roof height, that doesn't mean it's the mean roof, it just means the average height of the roof. And that's not too hard. If the lowest point is 10 feet, the highest point is 16, the mean roof height is 13 feet. Okay, and that's what ASCE uses for definitions of various coefficients that they use. You need to know the zone. And what we're trying to do is, what is the estimated force here? The risk category, we're going to talk about what all these things are. The exposure category, we need to know about if there are any escarpments. That's a fancy word for hills. How big is the module? Because bigger modules tend to be less likely to blow away. Slope of the roof. Oh, and finally, the speed of the wind is also important for doing a wind load. Who would have thought? So what are risk categories? We'll go through these kind of quickly. Number 1 is structures representing low risk of human life. Number 2 is everything else that's not specified in 1, 3, or 4, like a house. 3 is structures that could be a problem to human life if the roof blew off and release toxic or explosive substances or something. And then there's category 4. And these are essential facilities like emergency service, hospitals, air raid stations, shelters, or hurricane shelters, stuff like that. Anything that you have to maintain its functionality. And these risk categories all require, progressively require more serious hold down design. To make sure that these things aren't going to blow away. And the way they work the risk categories is based on how many years do you expect to be between 2 events that would be classified. And it's all right there described nicely in ASCE 716, so we're not going to do that. Each risk has its own wind speed contour. So risk 1 might be 130 mile an hour. 2 might be 140, 3 might be 150, and 4 might be 160, for example. In other words, you simply have to beef up the design. The bigger, the higher the risk category. After you determine the design wind speed, then you have to calculate some stuff. You need to do this one. You need to find the QZ. 0.00256 relates to the density of air at sea level. KZ is a coefficient based on the height of the roof. KZT is a coefficient based on the terrain. K sub D is a coefficient based on the shape of the building. K sub E is a coefficient based on the change in density of air as you go up in altitude. And V squared is the wind speed. So interesting here, you notice that the solar production from a module is linearly proportional to the intensity of the sun, but the forces from the wind are proportional to the square of the velocity. So 141 mile an hour wind is going to give you twice the pressure as 100 mile an hour wind. Okay, so important. So 0.00256 is easy. Then you have to look up all these other coefficients for the location. All right, because once you got QZ, then it's easy. You just wait a minute. Where's QH? Well, QH is QZ evaluated at the mean roof height. So you have to calculate QZ at the mean roof height. Okay. And that is going to enter the QZ factor by means of the KZ, K sub Z factor. The GCP is a coefficient that depends on the location and the orientation of the module. And these are pressure coefficients, and there's one for uplift and there's another GCP for a downward force. And we'll take a look at some of these in a minute. The gamma sub E and gamma sub A are also some parameters that depend on how close is the module to the edge of the roof and what kind of a tilt might it have. So in other words, how high is it is it mounted above the roof? So the actual pressure, all we have to do is look up all these numbers now and do the calculation. Well, you know, it takes almost no time at all to do that when you've got a nice spreadsheet that has all the numbers, and you key in a few things and all of a sudden, bingo, you've got all your numbers for all of your different zones, because the spreadsheet has, okay, multiply QZ by, or okay, first find QH and now use the different GCPs. All right, so that's what we're just talking about. I could have written this down so you could have read it while I was saying it. Okay, so how do you get KZ? Well, you look it up. Okay, and for heights up to 60 feet, it depends on the exposure category, B, C, or D. So we'll assume this example we're doing is an exposure B, which is a standard residential neighborhood type house. And if the height in feet above the ground is between 0 and 15, it's 0.7. And fact of the matter is, all the way up to 30 feet, the exposure B coefficient is 0.7. All right, it's KZ. Exposure C, you know, that's a little more open space. And therefore, the wind blows a little harder. It's not going to have any trees or houses to slow it down. And exposure D is what I look out if I go outside and look to the east, because we've got a couple of thousand miles of ocean out to the east of our building. And so therefore, we are in exposure D. The coefficient is 1.03 for a low roof, but our roof happens to be 130 feet high, and it's not even on the scale here. So designing a system for our condo involves some pretty high and some pretty big numbers. Okay, so anyway, here's your KZ table, which comes out of ASCE 716. And then we get other exposure B, C, D. All right, we talked about what those are. And some counties in Florida, you can only use C and D. They won't let you use exposure B. Anywhere to the south of me is strictly, and to the just to the west of me, they're strictly exposure C. And this, as you notice, the higher you go, you have a change even between 0 and 15 feet. C is bigger than D, and above 15, it gets bigger to 30 and so forth. So the people in Fort Lauderdale, Miami, Boca Raton are really serious about the PV systems not blowing away. Here's these other coefficients, and you look them up in ASCE 716. And exposure coefficients depend on a lot of things. And in our particular case, the exposure coefficients are as follows, depending on the zones which are on our roof. Zone 1 plus 0.6 minus 1.3. Notice that the positive coefficient is 0.6 in every zone. That's the downward force. But the upward, the biggest one is in zone 2R, minus 2.1. So you multiply by minus 2.1. That's the minus sign, simply means it's an uplift force. And then we have these other coefficients, the terrain coefficients and so forth. And again, we look up what they are. Mostly flat terrain, KZT is just 1. For a normal structure like a house, but not a silo, for example, or a chimney or something that has an oddball shape, the K sub D is 0.85. And if the altitude is less than 1,000 feet, K sub B, if you use 1, it doesn't start really getting a lot smaller. The atmospheric pressure is kind of exponentially dependent on the height. And so it doesn't start dropping off until it's half as much at 18,000 feet. Y'all probably learned that in your science class somewhere. And with the slope greater than 7 degrees, the roof slope itself greater than 7, gamma sub E is 1 according to ASCE. And if the module is 18 square feet, gamma sub A from the little picture in the ASCE, you get gamma sub A is 0.7. So at 115 mile an hour wind, all these factors multiplied together is 14.1 pounds per square foot is the bottom line. All right, but now we have to start multiplying by the GCP factors. All right. So what do we get with that? Well, that's our final wind load determination. And so here's what we have for the 3 wind zones, 8.46 minus 18.33, and the highest minus 29.61 for this wind speed. However, if we start looking at Schedule C, 25 feet high, Miami, Florida, in certain other zones for non-hip roofs, some of these numbers get up really close to 100 pounds per square foot. And that's a lot of fun to design so they won't blow away. But in anywhere but Florida, the numbers are going to be more like what you see in front of you. And for this reason, the module frames don't have to be quite as robust, and therefore the modules themselves can be a little bit less expensive. Looking at the model number is really important from our standpoint, because we need to make sure it's the model that has the high wind resistance rather than the model that has the low wind resistance but sells for 15 or 20% less, or whatever the number is. I don't really know what those numbers are. I'm an engineer. Why should we know numbers, right? So anyway, we now can get all the overall forces on the module. Let's say we mount it like this. Then we put some mounts in. It's nice to spread your mounting attachment points so they cover all the different trusses. And so we notice that the top rail with the top 5 mounts, we got 2, 4, 6, 8, 10, 11 mounting points. And so then we do a little analysis here. And let's see what we get. Well, if you use 18 square foot modules, then we can get the module area in each zone. And top row, we got 54.9 square feet in zone 1, 35.1 in 2R. And using the numbers for those particular areas, total uplift on that group of modules in the top is 2,046 pounds. Next row, more modules in it. Total uplift 2,741. Next row, even longer. Total uplift 4,066 pounds. All right, so that's pretty straightforward stuff, and especially if you're doing it on a spreadsheet. So the average uplift is simply, we saw the number of mounting points in each row, 11 in the top one, 17 in the middle, and 21 in the bottom. So we've got 186 pounds per attachment point in the top row, 161 in the middle, and 194 at the bottom. So what does this mean in terms of the length of the screw or the strength of the attachment that you're going to use? Well, that's pretty straightforward too. Because if you use 5/16 lag screws, which is a common screw that you use to screw into a 2x4, then you've got a list of withdrawal loads. And down south, we typically have southern yellow pine, but there are some areas of the country where the rafters or the trusses might be different wood. But this gives, with the safety factor of 4, you can get 332 pounds per inch of embedment into the truss with 5/16 inch lag screw. If you go Douglas fir, you only get 198. Well, we're going to pick the southern yellow pine and 332. And what does that do? Well, wait a minute. What happened? Where did my goodness, I lost the bottom bar here. I don't know where that went. How strange. Well, in any case, given the pull strength of 332 pounds per inch, we can go backwards and see here that if we've got lag screws embedded 1 inch, it will hold every one of these attachment points on every row, because the 332 pounds is more than 194, 161, or 186. So I don't need that other row there. We'll go back here now. And now let's talk about electricity. I think wind loading is fun, but I'm an electrical engineer, so electricity is even more fun. So let's talk about that. And let's also see what time it is. 3:19. I think we are probably going to make it here okay. All right, so what are the electrical options for this particular system? So let's do some example designs. We'll do one with microinverters, we'll do another one with power optimizers, and we'll do yet another one with string inverters, and compare the design procedure for these, okay? Now, every one of these inverters or optimizers, an optimizer is not an inverter, it's DC in and DC out, but it does have maximum power point tracking, so it knows exactly how much DC out that it needs, but it also wants to find the maximum amount of DC in. And all of the maximum power point tracking they work on the DC output of the modules. Okay, so let's see what we can do here. And rapid shutdown at the module level, that's another advantage. That's been pretty important since 2017, even 2014, but it's getting tighter and tighter. And now is necessary to, as of 2020, you have to shut down within the boundaries of the array. No more electricity outside where the modules themselves are. And you need to do that fast if you have an emergency. The firemen or whatever the first responders are, have to have a switch somewhere that they can flip that thing, and you lose all power coming out of the array within a couple of seconds. Okay, so it helps to know something about the inverters and what the IEEE 1547-2000 or Now, IEEE 1547-2000 is a standard. UL 1741 is a test procedure to make sure that the inverter meets the standard as laid down in IEEE 1547. So you see these things used kind of interchangeably. But UL 1741 is the label you want to look for on the inverter. So UL 1741 says you have to have good sine wave, okay? And it says that if the utility goes down, or even if the voltage drops below a certain level or goes under or over the frequency, 60 hertz by a certain level, it has to disconnect. And when it does disconnect, it has to wait 5 minutes before it reconnects again. And probably one of the most important, these are all important features as far as the utility is concerned, and the anti-islanding requirements. And this is where that current source part comes in handy, because the current source is synchronized by the utility voltage. If the utility voltage goes away, the current source loses its synchronization and it starts drifting, its frequency changes to the point where it goes out of range and the microinverter has to shut down, or the big inverter if it's a big one. Okay, the whole idea is that if you have 4 or 5 or 6 or 10 or 100 of these inverters all close to each other, you don't want one of them to think that the other one is the utility. But if all of them lose their synchronization signal, then they all go off on their own. One of them is probably going to be a little stronger than the other one way or another, and it's going to dominate, and it'll take all the rest of them down with it. So that's pretty important, because that way the world doesn't think that a PV inverter is utility. Now, this gets to be a problem with battery backup, and there's a way that's solved, but that's a subject of another conversation. Simply, the battery backup inverter has additional control capability to provide that synchronizing signal once the disconnect from the utility occurs. So then there's also possible control options with utility. The utility you might be able to sign an agreement. The utility can vary the power factor of your system up, say, between minus 0.8 and plus 0.8, or maybe they can vary, maybe they can turn on your batteries if you have batteries. With a straight grid connect, mostly what they want to control is your power factor, and not necessarily they don't necessarily want to reduce your output. Normally, if you're cranking out, they want to use everything you have available. All right, but they might want to use you to help them do some power factor correction, because that makes their system a little more stable if you can do that. So let's design a microinverter system. And I see we have a question. I don't know how long that's been there. I hope not too long. Are the disconnect requirements based on utility, over under voltage and frequency, or the inverter? They're based on if the utility goes over too far or under too far in either voltage or frequency, then the inverter, in other words, the inverter monitors the utility, and if when the utility is having issues, it's defined by the voltage going up, going down, or the frequency going up or down. And so the inverter has to be measuring that all the time. And as long as the utility is healthy, then the inverter stays up. But if the utility, it looks unhealthy, then the inverter has to shut down. Okay, so let's design a microinverter system. That's what it looks like from the previous picture we looked at. And let's look at some of the design rules here. First thing you need to do is match the microinverter to the module. And again, if you're interested in doing this, if you're not already doing it, you'll have the slides to read the rules on later. I'm going to go through them rather quickly. And we're going to do the match up here. So we'll just say, okay, here's the rules. Some are designed for 60 cell modules only, and others work fine on 60 or 72 cell modules. Typical module cell counts are 60, 72, and 96. Now you say, well, what about the 144? Well, the 144 cell is really 144 half cells, and the module is really two modules connected in parallel within the same enclosure, so that it performs like a 72 cell module, but more efficiently because of the 144 cell half cells. And again, I'd love to talk all day about that kind of stuff, but we won't get very many designs done if we do that, but it's really fascinating. So 60, 72, and 96. And we see both, but we see probably more 144 half cell type modules because they're the ones that are typically in the 20-21% efficiency range. And when you're putting PV on a roof, you generally want to put as much as you can, and the more efficient, the more you can put up there, usually, unless the geometry of the modules themselves is not conducive to the shape of the roof. So there's lots of little glitches here that have to be dealt with. The rated microinverter output. See, a certain microinverter, a 290 watt microinverter will only put out 1.21 amps, and that's it. And so no matter what, if the module wants it to do more than that because it's putting out more power, the microinverter says, sorry, I'm current limited. I stop at 1.21, that's it. Of course, that's really nice as far as designing this overcurrent protection, because that way, well, we're going to do it, okay? And typical microinverter output current are 1 amp, 1.21 amps, 1.45 amps, and what I left out is 1.35. Actually, I see more of the 1.35s than 1.45s, but I see more of the 1.21s than of the 1.35s. So, but those are some common ratings, and they're all at 240 volts. And yes, a lot of these can rated also at 208 volts. Modules rarely generate rated power, and we're going to show a picture of this a little ways down. Oftentimes, you can use, say, with a 290 watt microinverter, you can have 150% of that as the DC rating of the module. So you can go up to 440, even 460 watts with a 290 watt microinverter and not lose very much, because the actual power that comes out of those modules is typically less than 80% of their rating, just because of all those degradation factors we looked at earlier, the clouds, the temperature, the sunlight not being directly incident on the modules, and so forth. So a 1.21 amp unit, they can be used up to a 440 watt. Okay, I just said that. Okay. So let's just show some specifications here for a 400 watt module and a 290 watt microinverter, and show that the yellow match is okay. The maximum DC input can go up to 60. The 400 watt module has maximum 49.8 volts. And even when it gets cold, that maximum output voltage won't be much more than 15% higher. So that's going to be 7.5 volts up in northern Minnesota, somewhere near that town Cook, I guess it is. Gets down 60 below a long time ago before it started getting warm. But in any case, that's a good match on the yellow part. The maximum power point tracking range is between 27 and 45, and the maximum power point range in this one, if you go from the hottest to the standard, the lowest it gets is 35.5, so that's good, fits well within the maximum power point tracking range. Module short circuit current, maximum as far as the microinverter is concerned is 15, and we're at 10.36 here, so plenty of range there. Maximum output power Microinverter, most it'll put out is 290, maximum output voltage is 240. Well, maximum minimum, it's the nominal output voltage is 240, depending on what the utility is running at the moment. And so maximum system voltage with that module is 1500 volts. And we're running the system at 240, so I guess we're good there. So therefore, and note the microinverter efficiency is about 97%. That is, pretty impressive. And that's the weighted efficiency, the California weighted efficiency. That's operating under an average efficiency. The maximum efficiency goes up pretty close to 99% with these things. So we've got a match. We've got a microinverter matches with this module. And of course, there are several others that would also match, but we'll take this one for the moment. So now, it turns out these things go into a combiner box, because if you have maybe 4 or 5 different circuits, you want to combine them down into one, like you do in a distribution panel. You got some fat wires bringing a lot of power in, and then it goes out on the small wires. Well, here, the power comes in on the small wires and it goes out on the fat wires. It just works just the opposite of the distribution panel, and it's called a combiner panel, but it's the same geometry, same everything, pretty much. So how many microinverters can we have in a 20 amp circuit? Well, maximum output current is 1.21. The maximum continuous current for a 20 amp circuit is 16. So you can have 13 per circuit, pretty straightforward. So for a whole host of different modules, if you use this particular microinverter, you can have 13 per circuit, and that's it. And then you start another circuit. Now, the neat thing here also is that you can have one circuit of 13 in parallel with another circuit of 8, and they're perfectly happy because they're in parallel, and voltages in parallel are happy together. They're all at 240 volts. One will have maybe half the current of the other, but that's okay because the currents just add numerically, and so that's no problem. So that's another advantage here, is that you don't have to have the same string length here, just so you don't go past 13. So how are we going to do it here? Well, how about 2 circuits of 12? We got 24. How could we do that? Well, we put some there. There's one there, a couple more there, and there's 12 modules. A little fishy there because we got that one hanging by itself, but we're going to do 12. And let's see if we can put in 12 up here. Sure enough, 12 up there. And that means that each circuit's going to be 14.52 amps because we get 1.21. This is maximum now. Normally, it's going to be running less than that, but this is the max. So that's certainly within the 16 amp limit. And it might have been, see, what we could have done is we could have just put that number 1 in the middle row, could have been a 2. And it simply would have meant we have 11 and 13. And that's still okay. Because 13 is the maximum. And 11 is acceptable because anything less than 13 is okay. And it, from the perspective of the person wiring it up, it might be a little simpler not to have to make that extra bounce up to the top one. On the other hand, it's not necessarily that bad to make a quick loop up and down between the third one in from the right on the bottom up to that one on the second row and then back down again, rather than going to the end and then going up. So it's not so bad the way it is. It's certainly not something that, I mean, it's okay. We got 9,600 watt DC rating for the array. Listed cabling is provided by the manufacturer for hooking these things up, and they just snap together, and they're male-female type connections. You can be as drunk as you want and not make a mistake, but you got to be careful not to fall off the roof. And then these circuits are fed to a combiner box at the ground level. And so what happens down at the ground level? Well, here's the circuits coming from the roof. There's your combiner box. We got 2 of them in this case. And the combiner boxes typically have 4 circuits. That this is if we're using N-phase equipment. And you can do more than 4. You just don't use their fancy combiner box, but their data and communication module is in that box as well. And they combine the output, goes to a disconnect that sometimes is optional. Notice you got a neutral bar, you've got, and that neutral bar is there as a reference for the data and communication. These are all 2-pole breakers here for 240 volts. The unfused disconnect is optional if the utility requires it. If you're in level 2 of between 10,000 and 100,000 watt AC system, as far as utility call. And then we connect it to the utility. How are we going to do that? Well, one way to do it is to connect it by means of a backfed circuit breaker, according to NEC 705.12 B23B. I don't know how many times I've said that because we talk about it all the time. It's one of our favorite topics at work. Point is, it's called the 120% rule. And it says that if you insert your solar at the bottom, then 125% of the solar output plus the rating of the main circuit breaker, that 200 amp breaker up there, has to be less than 120% of the bus bar rating. Well, 36.3 plus 200 is 236.3, 120% of 200 is 240. So we're good. So we can do this, provided there's room for that breaker at the bottom of the panel. If there's room for one in the middle of the panel, maybe you can shift a few up and make this one available at the bottom. So this is one way to do it, okay? And it's very common. It was extremely common long ago, and now some more elegant, sophisticated ways of hooking in have been developed, and we're going to take a look at them as well. Time, what are we looking at? 3:38, 22 minutes. We're going to say 24 minutes since we started 2 minutes after the hour. Okay, so here's a standard diagram of how this thing be wired down on the ground. Maybe. Okay. Now these are all AC circuits, 240 volt AC circuits. Now, what if the 120% rule doesn't work? We can use a line size tap. So here's what we're starting with, but now we have to go to the point of utility connection, and we're going to do it this way now instead, okay? If, say, the PV plus the main circuit breaker is more than 120% of the bus bar rating, or if there's no room in that main distribution panel and you have to somehow or other tie it in, and if that's the only distribution panel they have, then maybe you can tie in on the line side of the main breaker. Sometimes you can't do that either because the main breaker is connected by a bus bar to the meter, and that doesn't work either, but we'll see what you do about if that happens. But here is your line side tap. Pretty straightforward. You just connect in as long as your PV does not exceed the rating of that feeder from the meter down to the distribution panel, you're good. So that's another way to do it. But sometimes you can't get to that line side of the main circuit breaker. So then what are you going to do? Well, you might do something like this. You use a load side tap. And what that means is you're going to tap somewhere between, you're going to add an extra 150 amp circuit breaker to the main distribution panel. And you've got your 150 amp main disconnect up there. And we tap right in between the two of those. All right, and what does that do for you? Well, it says that the most current that you can go down into that bottom panel is 150 amps. That's protected by that lower breaker. The most current you can get from the utility is 150 amps. Current doesn't go backwards into the PV system. The PV system is a source, so you only get power out of it unless you get a short circuit there and if the system fails, and that's why you've got fuses there. That fuse disconnect never blows because the PV system did something wrong. It's because maybe the PV system had a short in an inverter, a short circuit, and then it's the shorting, it's the current that comes from the utility that blows that fuse, not the current from the PV. PV is never going to blow that fuse because that fuse is sized at least 125% higher than the maximum current that's going to ever come out of the PV system. All right, so here's your line side tap, and that's our load side tap. And it's a fairly, I don't know what fraction of our total jobs have load side taps, but I'd say maybe 20%. And it's when nothing else seems to work. You may do, and if you, there are times when you can't even put in this may be a main lug only distribution panel down there where you can't add that extra 150 amp breaker. So then you add another panel that you can add that 150, and you go from the meter down to the new panel and then out the main lug, the lugs on the bus bar out to the original panel. So there's lots of ways to solve this problem. And just wanted to let you know that there's just a lot of stuff out there, and they're pretty neat the way these things work. And so 705.12 B22, and there's 705.12 B23C, which is also really neat, and a couple others, but at least you can see that there are a lot of different ways to do this. And if you get into business, you'll learn them quickly, believe me. So there's special rules on any loads connected between 250 amp circuit breakers. If there were loads between there, but as you see here, there are no loads connected at all. This is just a PV source. So how about designing an optimizer system? How are we doing here, Roger? 343. Okay. Well, here's your optimizer system that you saw earlier, and I'm sure you all memorized it and remembered where every plus and minus sign was, but thought maybe we'd take a look at it again, okay? And of course, how do you design one? We have to have rules. And here's something about the optimizers, and you can read all this stuff. The fact they do their own maximum power point tracking individually for individual modules, except for the optimizers that are built to do 2 modules at a time or 4 at a time. And that holds true also for microinverters. So sometimes they're not just working with 1 module. Sometimes they work with 2, 3, or 4. But those haven't really caught on that much right now. And I'm not saying use them or not use them. Look at the specs and the warranties and availabilities and prices and all that kind of stuff. And that helps a whole lot in trying to make a decision. But notice the series connections here. The black wires are ground wires. That DC from the junction box to the inverter really could be, it consists of a ground wire, and the black is negative, not ground wire. I'm sorry, I made that mistake. That's a bad mistake. But anything that's at anything more than 0 volts is indicated by a red line there. But each optimizer has a plus and a minus, and they're put in series just like batteries in a flashlight. Plus ends all pointing to the left on these things. Okay, and then they're connected in parallel. Go to the inverter, DC coming down, inverts it, and then there's a disconnect if required by the utility. Maybe there's a disconnect is going to be just a circuit breaker in the distribution panel. Number of different variations. So each string has the same output current and the same output voltage. Well, actually, each string doesn't necessarily have the same output current, but each string does necessarily, on a string level, have the same output voltage. Okay, but the currents add up, the voltages stay at whatever it is, 400 or so. So, some rules. You have to match the optimizer to the module. Okay, that makes sense. You might have different numbers of modules. And optimizers, see, in a microinverter system, you can go down to 1 module as a string, but in an optimizer, there is a minimum number of modules and it's limited by the maximum DC output voltage of the optimizer. If the optimizer is limited to 60 volts out, and if the system's going to operate as high as 400 volts, then you got to have enough times 60. And, 5 times 60 is 300. It looks like you're going to need 7 optimizers in order to get up to 8 to 400 volts. So minimum string length here is 7. In order to get your 400 volts, you need to make the inverter happy. Okay, so You can have different number of modules, but the flexibility is not quite as much. And there's also minimum voltages where the optimizers will work with maximum power point tracking. So that means there's a maximum number in the array. And again, the matching says the array power can't be more than 155% of the rating of the inverter. And again, there's just one inverter in this system. The optimizers are DC to DC creatures. Okay, so matching the module to the optimizer, same drill, and you just make sure that the orange stuff is acceptable for the orange stuff coming out of the module. You don't have much control of once you select the module, but you then have to select the optimizer to match up with the module. All right, and once you do that, then you select an inverter and how long the circuits can be. So the array plus the optimizers, you're looking at 9,600 watts. So if the input power is 400 watts for the optimizer, and the output maximum, it can be 15 amps, then that would be a voltage of 26.7 volts. And so that's how low the voltage might go with full output current. All right. And so the output is more than 26.7, and if the output current is less than 15 amps, then with the same input power, if the current goes down, the voltage has to go up. Very simple. The inverter does the controlling of these optimizers. And so for these particular 400 watt units, the minimum voltage is going to be 26.7. So if we divide 400 by 26.7, it says you don't put more than 15 in this string. Otherwise, it's simply, in some cases, it simply won't run at maximum power. And sometimes you can actually damage the inverter. So you have to be careful of things like that. So if you have two circuits of 12 this time, then if you have 7,600 watt inverter, 400 volts, 15 amps, the maximum power for either of those two circuits would be 6,000 watts. Okay, here's the 7,600 watt inverter. I use that because that's a very common one, but they come in a lot of other sizes. 11,400 being another common size. And again, we're matching up the devices so that they're happy working together. Okay. Now the modules and the optimizers, they operate independently, so orientation and shading are not a big issue. You can have, in one string, you can have some modules pointing south, some pointing east, some pointing west if you want to, or some shaded and some not shaded. And the modules and the optimizers, they do their thing to optimize the output from each module and keep the inverter happy by adjusting the voltage to what the inverter would like it to be. So we already did this thing, 7 minimum per circuit. So any number of modules between 7 and 15 is good. So what about the circuits? Well, if we've got that same 400 watt module, and if the circuits are limited to 15 amps by the optimizers, they're still usually wired with number 10 wire. And this PV guys like number 10 because we used to always do that. 15, 20 years ago, the circuits were almost always wired with number 10. Even though the outputs of the modules were nowhere near that, but the reason was simply less power loss, less energy loss in the wire. And when your modules are $100 a watt, you don't want to lose one drop of electricity. So you use fat wire instead. And that's kind of carried on as a tradition, even though with 15 amp circuit, you could use number 12. Well, two circuits of 13 and 11 would look something like this. Well, you already know, there's your 11, and here comes your 13 up here. And there you go, just like that. That's about how fast these things go in. And as long as you got a lot of people on the job who aren't tripping over each other. Each circuit's about 400 volts, the rate's 9,600 watts. Optimizer to optimizer cabling is provided by the optimizer manufacturer, so it's an all UL listed. And it's open wiring, by the way, no conduits or anything, just open wires and proper cable management configurations. There's a junction box on the roof where you take these open wires and you run them into the junction box and come out through conduit to the inverter. And so what's at the ground? Well, this looks familiar. You got an inverter that matches the stuff on the roof. A disconnect, and you might connect it up like that. Or that looks familiar, doesn't it? The old familiar backbed circuit breaker, or you might try one of these, line side tap, or maybe one of these, a load side tap. One way or another, you're going to get that thing tied in so that as long as your PV doesn't generate more current than your utility feeders are rated at. Let's say you got you have 150 amp coming in for the utility, that's your maximum amount, then you can't try to send more than 150 amps back to the utility. And I had one, yeah, just a day or two ago. There's a huge system for the 40,000 watts, had a 200 amp breaker connecting in instead of a 40 amp breaker, and that was into a 200 amp service. So the actual output of the system was around 160, but still, it's pretty close. But couldn't go much higher than that because you'd have to have a service change in a bigger service, and the utility may or may not go along with that. Okay, I've been talking about DC to AC ratios. In other words, the size of the array in watts is a whole lot bigger than the rating of the inverter in watts. And let's see what the losses are. I did some simulations with the 290 watt microinverter, and with a number of different modules. Okay, and here's what we get in terms of kilowatt hours annual output for a 290 watt microinverter, depending on the size of the module connected to it. And what you see here, it is not, and this is Orlando facing south, 18-degree tilt, no shading, NREL, SAM Advise model. And isn't this interesting that we have a nice straight line, nice linear output? So even though that 440 watt module never runs at full capacity, connecting a 440 watt module to a 290 watt inverter is going to give you proportionately more annual kilowatt hour production than connecting a 390 watt or a 330 watt. All right, so your annual production is still pretty much linearly dependent on the size of the inverter connected up to a limit. And after a certain limit, and you can determine that limit by using specific components in the NREL simulation. So this is pretty neat to see that. Okay, let's don't use microinverters or optimizers. When so where would you have a situation like this? Well, normally this is what you have with the big systems. You know, you get up to a megawatt or something, it's going to be a ground mount then probably, or even it's going to be a roof mount on a flat roof that does not any shading, and all of the modules can be strung out in strings that have the same exposure. So you don't need the fancy stuff. You don't need the microinverters or the optimizers because your modules are pointing in different directions, or the clouds are shading, or trees are there, or anything like that. So a quick run through how you would do it that way. How many will fit on the roof? That's one way. For string inverters, if you use more than one string, you really need to have the same module count for every string, unless a lot of the inverters now, a lot of the string inverters will have multiple maximum power point tracking inputs. Some of them will have like 2 maximum power point tracking inputs, and each input can have 2 strings attached to it so that you can have say 20 amps per input or 22 amps per input, depending on the inverter size. So you don't totally give up on having one string on a south roof and one string on an east roof if you have separate maximum power point trackers for each roof. That's all you have to be careful of with this kind of a system. Then calculate the maximum open circuit voltage. You don't have to do this with the maximum microinverters or the optimizers, but here you need to do it because you need to make sure you don't damage your inverter by having the string voltage go too high on that cold winter morning and actually damage the electronics in the inverter where it's only capable of handling, say, 600 volts max or 1,000 volts max or 1,500, whatever the case may be, depending on the size of the system. Okay, so then turn on the maximum number of series modules based on the open circuit maximum voltage at the coldest temperature and the maximum rated input voltage for the inverter, which if it's a house, it's probably going to be 600 volts. Calculate the minimum of the maximum power voltage. And that's because if the maximum power voltage drops too low, then the maximum power point tracking inputs don't track maximum power anymore, and you don't get the maximum out of the system. So the minimum of the maximum power voltage could be as low as 85% of the standard test condition, depending on how hot it gets. The maximum of the open circuit voltage depends how cold it gets outside, and the maximum or the minimum of the maximum power voltage is determined mostly by how hot it gets. And so then we can use the minimum maximum power voltage to get the minimum number of series modules, and the minimum, of course, it depends on the inverter maximum minimum MPPT. I'm getting too many M's here. I'm getting a little tongue-tied. Okay, and you need to confirm the inverter size by calculating the total array power at standard test conditions. And so again, you do it, the same old thing, pick a module, determine the voltage extremes, and if you, here's the formula, okay? So I know you've been waiting for formulas, and I'm sorry, I hope none of you fell asleep before this one popped up, but 49.8 is the standard test condition open circuit voltage of the module. And the 0.0028 is the temperature coefficient. And the 45 degrees is the difference between standard test conditions and the outdoor ambient. Maximum value, 45. And so notice that the voltage goes up from 49.8 to 56.1, which stayed below that 60 volt thing. But here's your formula for the people looking for the formula. Love to, and divide 600 by that, 10.7 modules. Well, you better not put in 11, better limit it to 10. All right, and now we go to the high temperature thing, and yeah, you can assume the hottest temperature will be 65, or you can calculate it. But if you got 45, this is a reasonable number though for pretty much everywhere except the Southwest. And everybody gets 95 to 100 degrees in the summer. So then the modules heat up a certain amount above that. And this, of course, is degrees C instead of the 27 degrees C at 98.6 degrees Fahrenheit and so on. In any case, that's 40 degrees C hotter. And here's the formula you've been waiting for. 40 degrees and the coefficient for the maximum power or pole voltage, again, negative, but this time we're subtracting from 1 instead of adding to 1 as we get warmer. And so we're dropping from 41.7 to 34.9, which means 7.02 modules to reach 245 volts. So you put 7, you're asking for trouble maybe 1% of the time. So if you want to be really sure you don't mess up here and stay within that window, you're going to put in 8. Okay. 7.02, that's pretty close to 7, and it's not going to give you a problem very often. If you really press for space or whatever, you could do 7 as a minimum, but 8 would be a better number. It's somewhere between 7 and 10 would be the number of modules in a circuit. So it's not that big of a range, 7, 8, 9, 10. There's only 4 choices of how long your strings can be. And that's important because you could have 3 circuits of 8 and get 24. In fact, the matter is that's the only way you can do it with 24 modules is 3 circuits of 8 and stay within that range, okay? So look for an inverter that will work with 9600 watt array, and if your DC to AC ratio is 1.4, then the inverter, you just divide 9600 by 1.4, leaves you with 6857 as a possible size for an inverter, and see when it's out there. Well, there is a 7,000 watt inverter that would work, so maybe we'll pick that one. And has maximum power range from 245 to 480. That works. Output rated current 29.2 at 240. That's a 36.5 amps that you have to size your wires to. You can do that. Use a 40 amp circuit breaker. 3 independent maximum power point tracking inputs. Well, so how nice. We can have those strings on different roof planes if you want. So here's a case where we've got 3 groups of 8, 1 for each string. And that way you could have a string having different orientation, or in fact, you could have 1 string of 7, 1 of 8, and 1 of 9, if they happen to come out that way, and each would have its own independent maximum power point tracking. So thing you can't forget is you need a rapid shutdown system, and there's lots of different options out there, but the nice thing about optimizers and microinverter systems is the rapid shutdown is right there built into the optimizer and the microinverter, and as soon as they see the utility is lost, which can be simulated by shutting off a switch that cuts off the utility feed from the PV system, then the array thinks the utility's gone and it shuts down. So that's a pretty convenient thing, but you can also do it with straight grid connect. By the way, the maximum power point tracking and the rapid shutdown, the rapid shutdown is only required if it's on a building that's occupied. If it's out on ground mount, then you don't need that, which is another reason why the straight grid connect things without any fancy optimizers or microinverters are more commonly used on ground mount type systems. So I'd say my granddaughter and my grandson appreciate your attention today. My granddaughter is now the mother of my great grandson, and my grandson just got his degree in mechanical engineering, and he's out working for a living and just bought himself a house, and he's going to put a PV system on it. And he just bought himself a new Tesla as well. So in any case, that's it. And these guys will appreciate it if we all do our job and get lots of good solar out there. So that's the end of the slideshow. I see a Q&A here. Let's see what we got. I see a thank you from Giuseppe. Thank you. Thank you for being here. I appreciate it. And I hope everybody got what they hope to get out of this. And if you didn't quite get it yet, then make sure you download those slides and go through it again. And if you have questions, you can ask questions to me through our host. And if you look at the chat box, the question about how do we get a copy, yeah, PDH source is typing the answer, and it's in the chat box. And let's see. Otherwise, I'm going to kind of watch here until the number of participants drops down to a low number. And at that point, I'll assume that there are no more further questions. And but I like to stay around just in case somebody has a last minute question they want to pose. Okay, we still have 36 folks. Oh, yeah, again, the quiz and certificate, that will be answered in the chat box. And I'm sure the host will answer that very soon. In fact, it was there at the beginning of the session. Check the chat box for all this administrative stuff. That's where you'll find it. You're very welcome, Nick. As I mentioned, for those who are still there, there is a follow-up session on battery backups, and all this stuff is kind of like a good prerequisite for understanding how the battery backups blend in, especially if you have an existing system that's not a battery backup. If you want some more information to help you with that, you can send me an email by way of the post, and I'll be glad to respond.